Okay. So my topic is let's play Hanabi. In this lightning talk, I would like to deliver 3 messages. First, Julia is easy to interact with other languages. Second, Julia is productive to provide HTTP services. And third, Julia is fast and easy to use for reinforcement learning related research. So what is Hanabi? In short, Hanabi is just a cooperative card game. Each player can only see others' cards, and in each turn, one can choose to give a hint to other, or play a card, or discard card. For example, here the player B wants to tell the player A that he has a card G4. So she can just tell him it's a green card. So the A thought it must be a G4. Then he chooses to play the G4 to the stack. So this is how the game works. To play such kind of games, we need to have a game engine first. Generally speaking, we can write the engine in pure Julia or write a wrapper in Julia. Fortunately, the DeepMind has open sourced the implementation. As you can see, the original implementation is written in C++, and some C interfaces are also provided. The Python wrapper is written with the CFFI package, and similarly, we can also write the package with clang.jl. As you can see that we only needed the following 4 lines to generate a wrapper. One thing I would like to remind you is that never forget to add a finalizer, or you may encounter the out-of-memory error. Now we have a game engine. Usually we would like to publish it as a web service so that we can play with it with our friends online. And with the help of the WebSocket in the http.jl, within less than 200 lines, we can write a WebSocket service. Then we can play it through Julia REPL or within the Julia Jupyter book, and we can even play it on the Teams. It's an internal product. What's more interesting is that we can train a smart agent to play this game. In fact, there's already a Python implementation in the original repo named Rainbow. But the source code is kind of verbal, so I rewrite it in Julia. The Rainbow is a collection of 6 kinds of games, and among which the most effective one is the distributional reinforcement learning. People also call it C51. So C51 acts just like other traditional value-based algorithms. It takes in the state of the environment and then feed into a neural network. Here I use a 3-layer dense layer. Then what makes it distinguished is that the output is the distribution of the reward. Here is the performance comparison between the Flux and the TensorFlow. The experiment is taken on a virtual machine, typical Azure virtual machine with a V100 GPU card. So when I finished the experiments, 3 questions come into my mind. That the first one is the Flux implementation runs much faster on this GPU, as you can see, but it runs a lot slower with only CPU. But how could it be possible? In fact, it turns out that the TensorFlow will utilize multiple CPU as much as possible. So when I rerun the TensorFlow version in a Docker environment and allocating only 1 CPU, the training speed decreases from 251 to about 200. Another trick used in the TensorFlow is that the staging area. By doing so, it can prefetch the next training batch while training for the current batch. And it is reported that by doing so, the training speed can increase about 30%. Unfortunately, I haven't figured out how to implement it in Julia. The second question is, did I use some special tricks to make Julia run much faster with GPU? And the tricks is, I found that I just encountered the following line, and it all runs very fast. But how could it be possible? The network is very easy. It's just 3 dense layers, except that there's another step named projection to make sure that the algorithm satisfies the Bellman function. And this is the equation for the projection step. Above is the Python code, and below is the Julia code. I must admit that it did look like some trick for those Python users, but I think for Julia users, it's quite easy and straightforward. Most importantly, it runs fast. Another trick is use views to enable that the data generated are sending to GPU directly. The third question is it always so fast? So I rerun all the experiments on my desktop with a 2080 Ti card. And as you can see, the GPU, within the GPU, the flux runs even faster, about 5 times faster. And here are the results. As you can see, these two methods all have a similar performance. While developing this package, I will receive an email that whether I could share the model. Maybe the next time I can reply that, how about giving Julia a try and get some free speed up? So this is my talk today. Thanks. Any questions?
Any questions?
Okay.
So I see. I mean, after you've tried to do your tweaks, it got even worse, right?
Oh,
Like flux was actually slower, even slower than TensorFlow. Like if you go back to the previous slide, yeah. So now this was like twice as slow, and like, oh, this is faster, steps per second. Oh, okay. Oh, right. Yeah.
okay. Cool. Thank you.
Yeah, I had a question about that projection step you mentioned, right?
Okay.
So you said you had the output from like a 3-layer neural net, right? And then you had to satisfy like a Bellman equation, right?
Yeah.
Could you elaborate a little more on how this works and like what we're looking at here? Well, like just what is being projected onto what?
You mean this step?
Yeah, I think so.
In fact, it means if we, it's a little complicated to explain it easily, but to make it simple, that we need to make sure that the original reward and the reward we predict, the original reward is in a range, and the predicted reward is in another range. So we want to make sure that this range could be in the same range.
I see.
So we need a projection step.
Gotcha.
And
Okay, sweet.
so you can see the paper for more detail. Just a document here.
Oh, nice. Okay. Thanks.
Thank you.
So let's have it for Tian.